Hi guys, wanted to do a screencast of the remainder of our derivation of the Poynting Theorem, and just for the sake of completeness I'm going to start at the beginning again. The idea is we have some volume V, we'll say, and inside that volume there is some charge and some current, and there's electric fields, and those electric fields are interacting with the charges and currents, which themselves are generating the fields. And we would like to know how much work is done in a small amount of time, an infinitesimal amount of time, by the fields on the charges. So if we look at a small piece of charge, consider the work done on a small part of the volume. The work done there would be the force applied dotted into the displacement of the charges. And as we said last time, the force is just by the Lorentz force law. It's dq times E plus V cross B. And that whole thing dotted into dl. But dl is itself just V dt, and we know that V dotted into V cross B yields 0, which makes sense. Magnetic fields do no work, and so this amount of work is going to end up being E times V dq, or dotted into it, times the dt. But we know from last semester, or E&M, that rho times V is J, and of course dq is just rho d tau. So we pick up a rho. Rho times V is just the current density, and so we end up with this work done on a small portion of the volume being equal to E dot J times d tau dt. If I now want to know the rate at which work is being done in that little piece of volume, I just divide both sides by dt. And if I wanted to know the amount of work done in the entire volume, which I would integrate over the entire volume, this expression E dot J, and that would give me the time rate of doing work, or the power expended, or the power delivered per unit volume. Actually, the total power delivered to the entire volume by integrating over the total volume. The question is, where does this power, or where does this energy come from? And to determine that, we have to do some manipulation. And so I don't want to go through the entire derivation. I'll do a couple of the steps, and then I'll refer you to Griffith's. Actually, it's probably easier if I just take you to Griffith's chapter 8, page 358. So here's our E dot J. And now we're just going to use Ampere's law and some vector identities. And you can see that if we work through the vector identities, use a couple of Maxwell equations, eventually you can come up with this expression, which is called Poynting's theorem, which is what we want to take a closer look at. So again, if I write this over here, the integral of E dot J over the entire volume, whatever that volume might be, this represents the power delivered to all of the charges in volume V. In other words, the rate at which work is done on them. If we take a look at this term, you should recognize this term in particular. This is the amount of energy stored in an electric field that has an amplitude E. And likewise for a magnetic field B. This one we talked about in the first semester of E&M. We did mention this one, but we didn't do much with it. But we did, however, do a couple calculations with this. So this 1/2 epsilon naught E squared is the energy stored in the fields. Because this is a time derivative, then this must represent the rate of change in the energy stored in the electric and magnetic fields inside our volume. And this negative makes sense if we're delivering power to the charges in this volume. If the fields are doing work on them, in other words, then that should equal the negative of the time rate of change of the energy stored in the fields. It has to come from the fields. And so what does this third term represent? Well, if you look at it, this is the dot product of E cross B with the surface, the area that bounds our volume. In other words, dimensionally, this has the dimensions of an energy flow through a surface. Energy per unit time per unit area. This statement then, this is conservation of energy for electromagnetic waves. And if this is the total work, time rate of work, total power delivered by the fields to some charges in a volume, well, that's going to equal the amount of energy that we lose out of the fields, the work that they do, but it's also going to be any energy that flows through the surface will also have to be taken into account. With the minus sign there, simply because if E cross B is parallel to dA, that means energy flows out of your volume, so you're losing that energy. Whereas if E cross B goes into your volume, it's anti-parallel to dA, so you'd pick up a minus sign here, which would make the whole thing positive, meaning energy is flowing into your volume. So again, this is conservation of energy. This is what each one of these terms represent. This is Poynting's theorem, which is just conservation of energy written in terms of electromagnetic fields. It's that last term that represents the energy carried by the fields per unit time, per unit area. And so we call that the Poynting vector. And this is an extremely significant quantity when you analyze energy flow in electromagnetic waves or light, because this is telling you how the energy is carried. In fact, we want to take a closer look at that, rewritten in terms of the general formula or expression for an electromagnetic wave. In particular, remember the E cross B. Well, B is related to E by this expression. And so E cross B ends up being given by this. So that tells us that we can write our Poynting vector as 1 over C times mu naught E squared in the k hat direction. And E squared is E dot E, so I don't need the vector sign anymore. If you use the fact that C is 1 over the square root of mu naught epsilon naught, you can also write this as C epsilon naught E squared k hat. And so what do we learn from this? Well, first of all, you see that S is proportional to k hat. In other words, the k hat direction, the direction of the wave vector, is the direction that energy flows in, which is something we've stated as being true, and we've taken for granted. Well, now we've actually proved that k hat is indeed the direction of propagation of the wave, or the direction that the energy flows in. Another thing is that electromagnetic fields oscillate at about 10 to the 15th hertz. We do not have detectors that can measure the instantaneous energy density, because nothing can keep up with that. And so from an operational standpoint, we typically deal with the time average of S. We use a silicon photodiode or a bolometer or something else to measure the energy in a light wave. We're generally measuring the average power, not the instantaneous power, and so that's the time average of this expression, where I've used the actual E naught cosine, the sinusoidal expression for E written out, simply to indicate that, hey, we're going to do the time average of a cosine squared, and we know the time average of a cosine squared is 1/2. One sidebar, if you're going to use this in complex exponentials, this works out. You get this factor of 1/2 if you write things out in sinusoid, because you get the cosine squared term. If you do not use sinusoids, then this E squared is E dot E star. And so your time dependence goes away and you don't pick up your factor of 1/2. And so typically you'll see S written in this manner if you're going to use complex exponentials. So that we put the factor of 1/2 in explicitly ahead of time, because when you go to take the time average of this, you won't have a cosine term to give you that factor of 1/2. And so this is how we define the complex version of the Poynting vector. And so when you take E&M2 in grad school, typically this is how you'll see the complex Poynting vector. You'll see the Poynting vector defined as a complex value or quantity, and so you'll see it written like this. Again, the factor of 2 is put in there ahead of time, knowing that with complex exponentials, when we go to do the actual calculation, we won't get the cosine squared term. That would then give us the factor of 1/2. Next thing we'll look at is the Maxwell stress tensor, which is conservation of momentum for electromagnetic fields. Before we do that, I want to do a couple of sample problems that we'll do together in class.